How come only one third of the class? Where are the rest? We have a break before this. It's not. So you're lucky that I don't have it. What about the rest at the back? Is that 5H? Behind 5H, right? Who is behind 5H? I? Is it 5I? All of you should have a copy of the Alkanes notes and tutorials. Once you have your notes with you, it will be good if you can read through to have a better understanding of what we are covering today, instead of spending your time interacting with your friends. All of you have notes, right? If you don't have, then your camera have to run to the photocopy lady. Okay, let's start since I would expect people will stroll in along the way. We shall not wait for them. It's already 11:10. So what we're going to do today is alkanes. This is actually the first, or I should say the second topic in your organic chemistry. The first topic that you have done is Intro to Organic Chem, whereby you are actually given the different terms. You are actually taught isomerisms. Okay, all this will come in useful as you journey when you're studying for your organic chem. This year, next year. Okay? So the first one, this medicine, I think you have seen it before where Mr. Ho ended his lecture on last week. Okay, whereby it actually causes birth defects if you actually use the wrong one. I think he ended off with showing you a video whereby they found that it's actually because of the different enantiomer that you are actually using. Okay, on top of this, there are also other medicines whereby you actually have to use the correct enantiomer of it. If not, it will actually cause harm to human body. Okay, like the first one, the intervenol. Okay, if you use the correct one, whereby you use the D, then okay, you can treat the illness that you want to treat. But if you use the wrong one, it can actually cause blindness. So this one, I think it was mentioned previously, is whereby the enantiomer was brought up. Okay, so same thing here, alkanes, if you notice, a lot of the carbons here are actually saturated compounds. They are actually carbon. They have 4 groups that is bonded to that carbon. Okay, there is another one here. It's actually to treat arthritis pain. Okay, arthritis pain. But if you use the wrong one again, it's going to cause you liver failure. So actually, a lot of the medicine in pharmaceutical chem is actually used. Specific enantiomer is used. You cannot just anyhow produce and anyhow use. Okay? Okay, so now we go into lecture proper. I hope you are ready for the lecture. Yes, I understand this topic is not covered in the EOY, but that doesn't mean it's not covered in A-levels. We are not going to go through this again, and you don't expect your tutor to reteach everything. If you don't listen, that's your problem. Okay, and for those who are not aware, this topic is not tested in EOY. But that doesn't mean you don't listen. Must faster add the second half first. Okay, alkanes. So this is what we're going to go through. We're going to talk about the structure. Okay, naming, you have already learned it, so we are not really going to go through naming just very quickly. Okay, we're going to talk about the physical property. Hey, I start, you start. I score, you stop. You want to take over the stage? I'm okay. Anyone? You can come here, I'm fine. I can be your teacher assistant. Okay, we're going to talk about physical property in terms of melting point, boiling point, density, and solubility. For chemical properties, we will be focusing on FRS, which is actually the mechanism one of the mechanisms that you have to learn in organic chem, whereby how a halide is actually substituted into the alkane. Okay, so the first one we're going to learn a little bit more about alkanes. It is actually a saturated compound, like what I mentioned just now. Saturated means there is no double bond, there is no triple bond. Okay, each carbon atom is bonded to 4 other substituents. Okay, so it's a saturated compound. It is sp3 hybridized, meaning to say there is 4 hybridized orbital. Okay, and it will form 4 sigma bonds. sp3 hybridized. If you are still not very sure what is hybridization, please refer back to your intro to organic chem. Okay, because it is 4 sigma bonds, it will be tetrahedrally bonded with a bond angle of 109.5. Back to your chem bonding, whereby you need to know the shape. Okay, it has a general formula of CnH2n plus 2. This is for a straight chain or a branch alkanes. Okay, later you will see what I mean. Okay, so this one is the general formula. This is a cyclo. Okay, if I have a cycloalkane, meaning to say it's a ring structure. Okay, this is a cyclopentane, propane, cyclopropane 1, 2, and 3. 3 carbon, cyclopropane. Okay, so this is cyclopropane, cyclobutane, cyclopentane, and cyclohexane. If you are going to count the number of C's to the number of H, okay, you will notice that the formula, or what is written here, you will notice that the formula itself is actually not CnH2n plus 2. Okay, if you can see, it is actually only CnH2n. Okay, so this is something you need to take note. Last time, what you learned is that alkane has a general formula of CnH2n plus 2, but this time round, when you come to cyclo, it might not, or it is not the case. Okay, it is actually only CnH2n. This is something for you to take note. Okay, so the nomenclature wise, you will refer to your intro to organic chem if you are still not very sure. I think some of the classes have already started on intro to organic chem, so you will learn more about how to name structures. Okay, so your checkpoint 1, very quickly, just 2 structures there for you to draw. I want the displayed formula, meaning to say I need you to show every bonds. Okay, I need you to show every bonds in the structure itself. So look at this, this is 2,3-dimethylbutane. So identify the parent chain first before you put in the substituent. Okay, so you can try it now, 2 minutes.
巧合一点。这个是如果它在这儿，它在这儿。
Okay. Are you done with your drawings? Okay, let's look at the first one. It is 2,3-dimethylbutane. So my parent chain is the butane, and at the second carbon and the third carbon, I have a methyl group. That's why we call it a 2,3-dimethylbutane. So you need to show everything. You need to show all the bonds. So please check. Okay, next, I have a cyclohexyl, cyclohexane. So same thing, first step, look for the parent chain. So in this case, it is a cyclohexane. Then a cyclohexyl in a cyclohexane. So what would you be expecting? 2 hexagons, correct? So I have a cyclohexane. Okay, and out of which 1 carbon, I have a cyclohexyl. Okay, so you show all the bonds in it. Which carbon you attach that cyclohexyl, it doesn't matter. Okay, because it is on carbon 1. Okay, but do remember to show all the bonds. You cannot draw your skeletal formula. It doesn't work. You have to show everything. Okay? Okay, let's move on. The second one. Okay, good. Yes. 1, 2, 3. Why no? It's just drawing everything. You don't need to show the bonds. You can draw your skeletal. Then you go back and draw in all the bonds. Learn to take shorthand or notes, people. Your NUS lecturer will not wait for you. Training in progress. So learn to take notes quickly. Okay, let's move on. Okay, next we're going to go on to isomerism. Okay, same thing, not sure, you can refer to it. Basically for isomerism, there are a few kinds. You have your cis trans, you have enantiomer, you have a positional. Then you also have your different structures that have the same molecular formula. Okay, so check point 2 again, very quickly before we move on. Can you try to draw all the structural isomers with this molecular formula? C4H14. And the hint is that there are 5. So you try it. Some of them are actually branch isomers. We go through your 5 isomers. I think some of you are struggling with the last one, thinking where is it? Okay, shall we look at it? These are the answers. Okay, I deliberately bracket the CH3 in red so that you know that it is actually bonded to this carbon. So you can check, the first one is a straight chain. Okay, I have C6H14, so I have 6 carbon, and then each one is just bonded to the hydrogen. Okay, next, which I walk around, many of you also have, whereby one of the CH3 is actually attached to the second carbon. Okay, the third one is where one CH3 is attached to the third carbon, because in terms of naming, it's different. This one is 2-methyl pentane. This one is 3-methyl pentane. So yes, they are different. Okay, the fourth one is actually whereby I have methyl group attached to the second, bonded to the second and the third carbon. So I will have 2,3-dimethyl butane. Okay, 1, 2, 3, 4 butane. Okay, the last one is whereby I have the methyl group. Okay, both bonded to your second carbon. So you will have 2,2-dimethyl butane. Okay, so this is your A, and out of which there will be one that is able to exhibit enantiomerism. Can you try it now and draw both enantiomers very quickly? The answers are here. Just need to decide which one is the one that can exhibit enantiomerism and draw it out. Okay, so out of this, which one is the one? It's actually your second one. Okay, the second one will have 4 different groups bonded to the carbon. Okay, so let's take a look. Okay, so your carbon, and then you have one group which is your propyl, 1, 2, 3, CH2, CH2, CH3, and then you have one that is CH2, CH3, one is H, one is CH3. And then there's a mirror image, non-superimposable mirror image. So I think some of you, probably your tutor will have already told you, CH3 is the only one that you can invert when it comes to a mirror image. When it is your CH2, CH3, or even your CH2, CH2, CH3, you are supposed to draw it like the way you draw it for the first enantiomer. There should not be a reflection of it. Next thing, when it comes to writing, you should write CH2, CH2, CH3 and not C3H7. Okay, I think some of you just shortcut C3H7. No. Write it as per the structure. Same thing here, C2H5, CH2, CH3, please do not write it as C2H5. Okay, this is something that you need to take note of. Next thing, when it comes to drawing, you also draw very clearly, this carbon is bonded to this carbon. Your CH2, CH3 should not fly anyhow. Okay, it should show very clearly that the carbon is bonded to this carbon atom. These are all the requirements that is stated. Okay, if you don't do it, you are at the mercy of the examiner. Okay? Next, let's go into enantiomerism in cycloalkenes, because this is something that probably you have not studied previously. Okay, so let's say I have this compound here. Okay, I need to identify the chiral carbon. When I want to identify the chiral carbon, simply means that I need to have 4 different groups bonded to the carbon itself. Okay, so I start counting. 1, 2, these two quite obvious. Then where is my 3 and my 4? 3 on the left hand side and 4 on the right hand side. This is how you can calculate for a cyclo compound. Okay? Okay, so then you might ask, how is it different? Why you say it's 1, 2, 3, 4 different groups? Okay, let's take a look. So if I'm going to count, if I'm going to count, like mentioned, this is one group, two groups. Okay, now the third one and the fourth one you count. From this carbon, you go to the next carbon. They are the same. Okay, fine. You move on. This one is different from this one. Can you see? This carbon is different from this carbon. So yes, so there is 4 different substituents. So this is your 3, and this is your 4. What? Oh, yeah, this is the pencil. Yeah, I use the pencil to circle it for you to see. Or should I use a marker, a thicker version? You only got pen. Or should I use pen? Is it better? What carbon, what 7 carbon? Checkpoint 2, why? 7. 1, 2, 3, 4, 5, 6, 7. What is mine? C6, H14. So it should only be correct one. 1, 2. No, this one. 1, 2, 3. Wait, what's wrong? What's wrong? 1. Okay, now I know what is it. Okay, fine. For checkpoint 2, please cancel the B. I think there is no carbon that is able to present an enantiomer. Because what I have in my answer is 7 carbon. So what you have is only 6. So yeah, so can you please cancel 2B? Checkpoint 2B. Okay? Okay, can you please cancel checkpoint 2B? So you just do for 2A. You just draw the 6 structural isomers. Okay? Okay, so let's proceed. Any problem? So you just basically just cancel your 2B. Just cancel your 2B. Yeah? Okay. Enantiomerism, I mentioned, there is 4. So you look at your first one, second one, third, and your fourth. So the third and fourth is by a difference of the BR. Okay, so you compare the carbon, they are the same, you move on. This one and this one is different. Okay, you compare this carbon and this carbon same. Okay, this carbon and this carbon different. Okay, so different, that means to say this is a chiral carbon. Okay, so you have a chiral center here. So you can just draw the two different. They are different. One is, if you look at it, one of the OH is pointing out of the paper, the H is pointing into the paper. Same thing, the mirror image of it, the H is pointing into the paper, the OH is pointing out of the paper. Okay? So sometimes you might be wondering which one should it be. Okay, which one should I be drawing my 3D? The cyclo part, okay, the cyclo part you will draw it as a normal line. It is only your substituent that you will use the wedge and the dash. Okay, checkpoint 3, I think you just need to find out how many other chiral centers are there. clue given, there is 3 more, wait, 1, 2, 3. Yeah, there is 3 more chiral centers other than the 3 that is given in the asterisk. Okay, let's go through first. This is the answer whereby there is 3 points. I think some of you even very puzzled why are the asterisks supposed to be there. Okay, so let's go through it together. One way to help you to ease your load whenever you are given all these big molecules is actually to eliminate all those carbon with a double bond. Because all those carbon with a double bond will not have a chiral center. Next thing, okay, I will always look for the complicated sites. Meaning to say, I will look at those that is at the junction to see if there is chiral. Okay, so this is one way to help you. Instead of going through every single carbon, okay, you can start from the complicated sites whereby there is seems complicated, there are a lot of different substituents attached, bonded to it. So let's take a look at this first one, chiral center. If this is a chiral center, I will expect 4 different substituents. So I start counting 1, 2, 3, and the last one is actually your hydrogen. Okay, so then you might wonder why different. If you look at it, this carbon is different from this carbon. Okay, and this substituent is also different from this substituent here. So yes, there is 4 different. Same thing, you go for this carbon. 1, 2, 3, and the last one is a H again. Okay, so you can look at this. Same thing, I look for the most complicated side. 1, 2, 3. And 4, the one at the bottom. Okay, this one with a double bond, I can forget about it. I will not have my chiral center. Okay, so you can do the same for the rest. Okay, let's move on. We're going to go on to the physical property first before the chemical properties. So all these are things which you already know, so I'll go through quite quickly. First one, the melting and boiling point, we are looking at it. The density and the alkanes are non-polar and insoluble in aqueous solution. Next, first one, melting point and boiling point increases. So the reasoning, same thing, let's go back to alkane bonding. We talk about structure, we talk about bonding. So I talk about structure, they are all simple covalent structure. Okay, because they are non-polar, so I talk about the intermolecular forces that is between the alkane molecules, which is your IDID. I talk about the strength because as it increases, the number of electrons also increases. So because of that, my IDID strength is actually larger and therefore I need more energy. Okay, this one is nothing new to you. Next, it is less dense than water. Yes, it's true. Okay, if you go and look at the density, okay, it is actually less than 1. Okay? It is actually on your page. Okay, it's not given. Okay, so the density, so this is the definition. Next, non-polar, insoluble. Because it's non-polar, it is not able to form effective interaction. And so because of that, it is not going to be soluble inside. All these are things which you already know, so you can read it up on your own. Chemical properties. Okay, non-polar, that means to say they do not have a polar bond. If you look at it, my alkane and my alkene, okay, they are very strong CC and CH bond. And finally, they need harsh condition. What do I mean by harsh condition? We can look at it later during when we are studying the mechanism the next lesson. Okay, so we are good with your physical property. Let's go on to your chemical properties now. I'm going fast because all these are things which you have already learned before, so you can just revise since you are already in the revision mode now. Okay, checkpoint 4. Okay, this is talking about the combustion. If you look at page 6 of your lecture notes, okay, all the combustion values are given there, and you notice that there is actually a trend. Okay, all the way from methane to butane. Okay, can you take a look at the trend and suggest an explanation for it? Okay, each molecule is increased by a CH2, if you notice. The increase in magnitude, okay, is actually because there is a differing, okay, from the previous molecule, it only increased by a CH2. So if you look at it, it's quite constant. Okay, it's increasing about 662. Whenever you increase there is an increase of a CH2. Okay, about 662 is approximately constant. Turn the page. The last one that we're going through before we end today's lecture is actually your free radical substitution. Okay, basically free radical substitution, if you notice, one of the H is actually substituted by a Cl or a halide, except fluorine. Okay? So it needs UV light because we mentioned before that in alkane it is a saturated compound. I have strong CC and CH bond. So I will need the UV light or heating in order for the reaction to occur. Okay? And the reaction does not take place in the dark, yes? Okay. Now I want to introduce you to a term called mechanism. Okay, not sure if you are aware of it, but basically mechanism is what we're going to learn in the subsequent chapters as well. So for a start, let's know what is a mechanism. Basically, it shows you the sequence of steps. That means it tells you how do you get to the final product. Okay, and in all mechanisms, you need to have the movement of electrons. Okay, there will be a transfer of electrons, and it is actually shown by the movement of the arrows itself. Okay? So before I start on my free radical substitution mechanism, I want to go through some basics with you, which is actually also already in your intro to organic chem, but I just bring it up here so that everybody have a common understanding before we go on. Okay, so first of all, I have a heterolytic fusion. What does it mean? Meaning to say I have this molecule, okay, when it breaks, okay, the electron from A is actually taken by B. So because of that, A will have a plus and B will have a minus. So I have A plus and B minus. Okay, and then I depict it by a arrow, a full arrow. Okay, so we call this the heterolytic fusion. Next, if I have a homolytic fusion, homo means one. So then what does it mean? When I break the bond, okay, each of them will take their own electron. Okay, so I will have a radical. This is what we call a radical. That means a A dot and a B dot. And notice the arrow itself, we call this a fishhook arrow. It is not a full arrow as compared to just now. Just now it's a full arrow, this is just a half arrow. Here we call it the fishhook. Okay, so this is to represent homolytic fusion. And each of the atom will just take back electrons. Okay? Next, if I have this reacting, what will happen? Okay, you will come, and then you will have your XA, and then you have your free radical of B. Okay? And the last one, if I have this again, okay, it can also be the B that forms a bond with your X, and then your radical will be your A. Okay? Okay? So then if now I have two radicals coming together, what will happen? They will just form a bond. Okay? Very good. Okay? So just to give you a little bit about free radical substitution, you have your RH, which is your alkane reacting with your X2. You need the UV light, like mentioned, okay, because it only occurs under harsh condition. Okay, so UV light is required. It is homolytic fusion. If we're going to look at the mechanism later, we're going to talk about it. And then it is a fast reaction. It occurs rapidly in the presence of the UV light. Okay, I will not go on further because I think if I go on further, it will take up some time. Okay, so we will stop here today. The next lesson, which is your term 4, week 1. Okay, first lecture. Please also bring along this bring along this notes. Okay, and